Hello. This is some work that I did with my colleagues from the École Polytechnique in Paris. Jaakko Sevdemon led this effort, and unfortunately, he could not come to Chicago. Um, the Greek diaspora metrics meta research concentration. So we are flooding with citation metrics, and some of them are more popular. In particular, H-index has been amazingly popular in lots of legitimate and mostly illegitimate uses. Um, these indices can be easily gamed. One can think of gaming by self-citations or by citations from fewer many authors. You can think of the H-index in a way strategically getting improved by adding citations to papers that if you just add one citation here and one citation there, it will maximize the impact on the H-index. Some circumstances may be more legitimate than others. And one can also think that some of the inflation in H indices may not necessarily be uh, lead fraud. It may be just focused collaboration among people who just work together, like in particle physics, or something in between, smaller collaborations or perhaps more fraudulent initiatives where people create cartels. So if you have strategic confrontation, that might be reflected in an inflated H index. Obviously, it will distort citation rankings. It will compromise the fairness and the accuracy of research evaluation processes. So we tried to see if we could develop some metrics that would have some ability to detect this type of strategic extreme concentration. And we came up with the term citation orchestration because you orchestrate citations in individuals or in groups. We use Scopus, the entire data set of approximately 1.5 million authors who have at least 5 papers and at least 1,000 or more citations until March of 2023. And we developed 3 indicators of extreme citation concentration, focusing on extreme values. We took the 1% of the distribution for these indicators. The first one may have extreme values due to small-scale orchestration. Second one may have extreme values due to either small or large-scale orchestration, like small team or single person or very large team or group. And indicator 3 will get extreme values in large-scale orchestration. This is the first indicator. I think it's the most simple, very easy to calculate. It's the ratio of citations divided by the square of Hirsch index. Very small values might suggest that citations have been strategically placed to specifically increase the H index. On average, this metric for the average scientist is about 4, but obviously there's a distribution as I show in that slide. And if you get a very low value, the 1% percentile is 2.45 or less, then this might mean that there has been some strategic placement either by the author himself or herself through self-citations or by a small number of scientists who act as a very coordinated citation cartel in that regard. The second indicator, which could manifest either with small or large-scale orchestration, is the alpha 50% C, and it measures the number of citing authors who cumulatively can explain 50% of the citations of an author. Very low values means that very few authors account for the majority of citations received. Most scientists get cited by a wide variety of people. It's not just few people who cite them. Of course, if they have a small field, probably they will have fewer people citing them, but it's unlikely that it will be just 1 or 2 people who just get all the citations to a particular individual. Now, we had to exclude here physics and astronomy from the classification of the scientific disciplines because it includes particle physics. We know that CERN does publish zillions of papers where you always have all the people being authors and all the people cite themselves, and this is completely legitimate in that environment. It suggests reliance on self-citation or very tight networks when you see very small numbers otherwise of alpha 50% C. And the third one is also a pretty simple indicator, alpha 50. is the number of co-authors with shared co-authorship exceeding 50 papers. We all co-author papers with others, but publishing 50 papers together with someone else really must be a very close relationship. And very high values might suggest either very large-scale collaborations where the authors belong to a big cluster of authors like CERN, of authors that heavily cite one another, or it could be other sorts of large-scale collaborations, maybe where authorship is an inflated commodity, that instead of having 5 authors in a paper, there will be 50 authors or 100 authors in that paper. And again, we get rid of physics of astronomy to avoid that confounding. And the 99% threshold is more than 7 co-authors having this very common pattern of more than 50 papers co-authored. So 1% threshold, of course, there's not exactly the same numbers because this is discontinuous measures. We have close to 15,000 authors below 245 for C over H squared. We have 11.3 thousand authors in the 1% for alpha 50% C and 12,000 for alpha 50. And there's different concentration in different scientific fields. So you see that the tails are heavily represented in chemistry, earth and environmental sciences, in the first index, chemistry, mathematics, and statistics in the second one, and medicine has its day in alpha 50, where you have some clinical and genetics and other bioscience collaborations having lots of co-authors. And this is very fine print, but you can see that there's a lot of differentiation across different fields. These indices also can co-occur. There's a very strong association between a low C over H squared and a low alpha 50% C, an odds ratio of 6.4. There's modest coexistence between a low alpha 50% C and a high alpha 50, and it's very rare to have a small scale orchestration index along with a large scale orchestration index, an odds ratio of 0.09. Now, that last combination, though, is extremely interesting. It's very rare, but a very large share of people who have that have evidence for retractions or things that could go wrong. If you look at the bottom of that slide, 45.5% of those who have indicators 1 and 3 have had retractions already. And I suspect that others will get papers retracted in the future. Conversely, 5% of those who have indicators 1 and 2, 2 and 3, or 1 only, 3% of those with indicator 3 only, and 1% of those with indicator 2 only. The average scientist has a little bit less than 1% chance of having a retracted paper at the moment. At the top, I'm showing you some other results from a parallel project that recently published in PLOS ONE, what I call precocious citation impact, meaning people who achieve citation impact in a composite citation indicator within just 5 years of publishing their first paper. They get to be in the top 2% of highly cited people, so something that the best scientists achieve usually within 30, 40 years of their career. Among them, there may be some that are really the best talents and the most amazing scientists in the world, but I think there's also a sizable group of people who are very problematic. So if you look at the proportion of people with ultra precocious citation impact and different indicators that may herald that behavior, the strongest indicator is orchestration indicator 1. So C over H squared, these people have very often, far more frequently than controls, such a pattern of small-scale orchestration, and many of them eventually end up with retractions. To conclude, extreme concentration patterns distort citation-based metrics. They do not necessarily imply misconduct, but these indicators highlight outliers and need to be considered in interpreting metrics. We can do that in large scale. We release information on the entire scientific workforce every year in collaboration with Scopus and Elsevier. Proposed metrics may serve as red flags for orchestration and deeper analysis and hints for association with abnormal publishing behavior and retractions. I think we need better evaluation of research impact beyond raw metrics, H-index, and related metrics. I think we need metrics to probe gaming of metrics. Thank you so much.
I'm Nihar Shah from Carnegie Mellon University. It's a fascinating study. Ideally, we would also want to use these tools to identify like maybe misconduct and so on. So towards that, I was wondering, like, is there any kind of a data set that you are aware of that could be used as a control group? That is like some sort of a gold standards vetted data set where you can be sure that, well, these citations seem genuine and we know there's no cartel and so on, and which could be used as a control group to identify like the thresholds, etc. in your work.
So in a sense, our design includes a control because we take the entire scientific workforce. So those who are in the different percentiles can be used as controls versus those who are in the extreme. We don't know really what is the best threshold. We picked 1%, which is very extreme. I'm sure that if you think of people who misbehave, some of them would be heavily concentrated in the tail, but others would be probably spread across lower or higher percentiles, more towards the middle. We do have these data sets now readily available. So also in linkage to retraction information, the updated citation indicators database that we release every year since last year includes very detailed information on citations from each of the listed scientists, along with citations to retractions and citations to retractions and so forth. Of course, retractions are also a proxy. Most horrible papers have not been retracted, and maybe a few good papers have been retracted. Um, but I think that this is a database in evolution that we can see how it plays out with new information and with new challenges also. I mean, we've heard presentations today about the rise of literature from countries with no democracy and probably high corruption. I think that some of these behaviors we do see specifically from these countries very often.
Thank you.
Ioana Krista Padova. I will ask something that maybe will sound a bit provocative, but looking at indicator one, for example, can't we say that things are, at least based on Scopus, not so bad? In the end, we hear all the time how everybody's gaming the metrics nonstop, and this is the only reason why we do research. But you looked at whole Scopus and you found 36 authors that are doing this. So, I mean, I know I'm exaggerating here a bit, and maybe it's also property of what Scopus's index is, but don't you think that this might also indicate that perhaps indeed misconduct, gaming, and so on remain at the periphery and not at the center, as many people are saying now?
Yeah, nice comment. I'm ambivalent about that because obviously in this work we did set a threshold ourselves. So we said 1%, but one might say, well, you should throw your nets more broadly and maybe go to 5% and 10%, or maybe be even more restrictive than 1%. And I think that there's a very active debate about what percentage of the literature is fraudulent or manipulated. Is it 1%? Is it 5%? Is it 10%? I think we need better information on that. I don't want to dismiss the 99 or the 90, conservative percent that is not fraudulent because 1 or 10% is fraudulent. So we have to be very careful. Sometimes in our wish to find problems and solve them, we forget that there's also lots of really great science, and and some of these metrics can work very well in many circumstances. I just see it as an add-on to metrics and as some extra protection to detect some aberrant behavior.
Thanks for the great talk. Tim Feeney, BMJ. I'm curious if you're able to use any of these metrics to predict who might end up having a retraction. I think that would be a lot more powerful for me to buy into this. And then I guess I would follow that up with, what should we do about this if we can predict that? I mean, do you start signaling out people that are at high risk of retraction and try to intervene at some point?
So in that other analysis that I showed briefly in PLOS, indicator one does have some predictive, actually, more predictive ability than anything else to predict people who will have retraction among a set of those who have very precautious, ultra precautious type of emergence in the literature. We didn't test specifically for the other two, so I cannot tell whether the other two would also have some ability to predict. I think that most likely these indicators highlight, as I said at the beginning, very different types of behavior. One is very small teams, and perhaps some of them are not as professional, versus very professional teams that are very widely organized and very solidly organized. It doesn't mean that they necessarily do good science, but they kind of occupy fields. So if the whole field is stuck to working in the wrong way, it will just get perpetuated with very little resistance. Again, retractions are a soft measure because it has very high misclassification, especially with missed retraction. But indicator one does have predictive ability.
Thanks, John. A question from Kristen Perry of the Melanoma Institute in Australia, wondering beyond astronomy and physics, if you can comment on differences in authorship and citation habits or expectations between different fields or disciplines.
There are clearly very large differences, both in expectations, in norms of authorship, on, for the same amount of work, there would be 5 authors in one field and 50 authors and 500 probably in a different field. So I think all metrics need to be adjusted and kind of taking into consideration what field we're talking about. We do that in the updated citation databases that we release. We have classification separately for each of 174 fields. So I think both the genuine metrics and the gaming metrics would have field specificity to some extent.